Okay, now, very often, this is a presentation, a small design we did many years ago of a city. By next week, I will bring in a local case study, because I just finished one design for an estate in Lagos. I just have to seek the permission of the owner of the project so that I can use it as a case study. So next week, I'll bring another case study, of a local case study. But for now, this is a case study that will give us an overview of what water design is all about. Once again, this is what we're going to go through in the next 10 weeks. We're going to talk about water reticulation in the first 3 weeks. We'll talk about stormwater and sewage design the following 3 weeks. Then we'll talk about road design the last week, the next 4 weeks. At the end of this class, I'm going to give us a timetable. I have it on my system, but because of want of time, I might not start going through my folder, but I know I have the program already lying somewhere, maybe on my WhatsApp, or one of my staff made it. But that suffices. I'll give us the outline by the end of today. I'll give us the outline. So this is a typical example of the steps you're going to take if you are asked to design a water reticulation system. What and what are you going to do? Now, there are two things here. Is either you are coming from the angle of the consultant, or you are coming from the angle of the contractor. But for this training, we are assuming you are the consultant. You are the engineering consultant, the civil engineer, mechanical engineer, who has an infrastructure engineer, which is what we are trying to create in the Nigerian context, because we don't have it in Nigerian university for now. So you are asked to design a water distribution system, a centralized water supply system, a water reticulation systems. All of them means the same thing. I'm just using them interchangeably. Whether it's a distribution system, a reticulation system, or a supply system, it simply means we want a centralized water supply network. So the first thing you need a map, you need a layout. And that map must have topo. It's a map and a topography. Okay, there must be some form of topo of the area. And why we say topo, it simply means the height, the elevation, because 90% of water reticulation systems are done based on gravity systems. Gravity system means you have a water source, you have an elevated tank or a storage source, and then you have a distribution network. So you must have a place you're going to take that water from, which could be a groundwater, a surface water, an artisan well, a water supply, a long distance water supply, or rainwater. So these are 4 different sources of water. So your job is to get the source, then you either put it in a holding tank, which is still a source, and then you take it to an upper reservoir where you can supply the water by gravity. The idea is that you need to reduce pumping costs. As an engineer, your work is not about providing services to people, but you must provide it within a cost model. You can't build a house of 20 million for 100 million and you say you're a good engineer. So water supply systems are always done based on gravity. That's why in your houses, you have an elevated tank. So that as soon as you on your tap, the water just comes out. So you need to have a map of the place. You need to have the topography of the place so that you can be able to know how the pressure distributes, because pressure is a very important parameter in your network, and pressure is a function of height. And because heights are fixed, they are rigid, you need to maximize them. You need to make best use of them. I know of a project in Mangu in Jos. The distance between the water source and the elevated tank, or the highest point within the catchment, is about 10 kilometers. But that is what they have. They can't help it because you must pump water to the upper reservoir so that during distribution, it will go by gravity. The next thing you need to do is you need to calculate your water demand for the people. And in calculating your water demand, you must take cognizance of three things. What are the basic daily usage of the riparian community? Are there expected growths? Are there future developments? Because in design, you must design for worst case scenario. So you must design for the maximum allowable water demand. And when we talk about designing for maximum allowable water demand, we are just saying you must project. If you are to design a water system, you must project 20 years, 30 years, 50 years. And that is the basis of your design. So if after 50 years, there's a problem with your design, you are justified because your design is meant to last for just 50 years. Okay? And of course, as engineers, you know that the higher your design horizon, the higher the safety factor. And the higher the safety factor, the higher the cost of execution. That's the common sense. Okay. Then the next thing you do is when you have computed this figure, this parameter of the different water demand, the growth, and every other parameter, you now sit down and calculate the various water demand. You now sit down and calculate the various water demand. After calculating the various water demand, you now move over to your design network and you now do the design. After doing your design, you now go and do the analysis. Analyze if there are places you have low pressures, if there are places you have zero flow, if there are places that you need to reject. So after doing those things, you now make your conclusion. So these are the very practical steps of doing your water reticulation design. So the first thing is introduction. What do you do in introduction? Well, you give a summary of the place you are designing. What is the location? What are the features of that place? What are the source of water? What are the population? What are the usage of the people? What are their work? Because all these parameters will influence their water demand. When you are doing water demand in a rural area, and when you're doing water demand in an urban area, it's a completely different thing. Like in Nigeria, in Federal Ministry of Water Resources, their specific water demand for rural area is 50, 60 liters per capita per day. Abuja was designed with 100 liters per capita per day, with a safety factor of 2.3. In other words, after estimating that each person living in Abuja will require 100 liters for a daily use, they still added a safety factor of 2.3. We are engineers, you know what I mean by a safety factor. Safety factor that will take care of population explosion, which we're having now, change in demand, change in land use, water losses, which stands at 40% today in Abuja. Yes, 40% of the water produced from Lower Usman Dam is lost. Go to me anywhere. And then other design inadequacies. All of us know that if you do your calculation or you do your design, sometimes you normally multiply your value by 1.2 or 1.1. Those of you that are civil engineers, you know what I mean. Or you multiply by a safety factor to take care of contingencies, what we call unknown. There are two types of risk when you're doing design. There is a known risk and there's an unknown risk. So the higher the unknown, the higher your safety factor. Okay, so that worst case scenario, your design will stand. So you need to define the place, describe the place. If you have a map of the place, you put up the map, show the streamlines, show where the water is coming from, show the geotechnics of the place, show the aquifer parameters, and every information that you need. Okay, apology, please. I'll move over to Intel. Okay, so you take a second look at the study area. You know, when you are citing a water scheme, there are some things you don't do. You don't cite a water scheme where there is problem, physical problem, biological problem, structural problem, or environmental problem. So your water source must be free from contamination. In fact, in ideal case, there should be a sort of meter radius where there should not be any activity. In a place like Germany, their waters, they give allowance a buffer zone of 50 meters. If they site a borehole, a water well here, 50 meters radius of that place, no agricultural activity takes place. Is a condition. So you don't go and cite your water scheme where there is landfill or where there is mining activity. Okay, I remember many years ago when there was lead poisoning in Zamfara because people were taking water from where they were mining things. That's by the way. But the idea is that you must study your area and you must define it. That is part of what you do as a consultant. You must explain the unique place, the hills, the topography, the difficulties, okay, the challenge that the contractor will face during that construction, because this is part of what will form the basis of your terms of reference. So what else do you do? You put a map showing how the catchment, how people are living in the catchment. Then you take a look at the study area, the industrial zone, how is it? The farm areas, how is it? The river, the road, everything about the area, you just speak the whole grammar that you can do there. So what next do you do? Sorry for all this. I think one of my staff did this and I didn't ask him to do all this. You take a section of the area so that you look at where there will be potential problems. If there are different areas that have different issues, you try to put them in a good place. You put them in proper, you show how the area is calibrated. The reason for this is that most times when you want to design a centralized water supply system, you find out that centralized water supply system is not possible. So what you do, you go for decentralized. Okay, decentralized simply means you have different boreholes, different elevated tank within the same layout, because you can't pipe from A to B or you can't pipe from C to D. So B will have a separate system, A will have a separate system, because it's just not easy. Because there is a condition that pressure must not be more than 8 bars. The pressure in a water distribution network must not be more than 8 bars. The reason being that the component of the system, such as your pipe, your pumps, your valve, some of them cannot withstand more than 8 bars. So in your design, if you are designing in a place and the pressure difference between one point and the other is more than 8 bars, it means you need to break the system. You need to zone the system into zones. You need to zone them. Okay. For instance, we all know that Pressure is a function of height. The difference between the highest point and the lowest point is more than 80 by 80. First of all, your surveyor need to go in, of course. Surveyor need to go in and take his topo so that you can have the place, topography of the place. So it was about 340, and the lowest point is about 220. So you can see that 340 minus 220 is more than 80. So it means that all of them, one pressure zone cannot work. So the next thing you do is that you break them into zones. Okay, those who are lying within a certain zone will become one system. Those who are lying in a different zone will become another system. Maboji, you have a question? I saw your hand raised. Or was it a mistake?
No, it wasn't a mistake. At some point, I don't know if I was the only one. I lost you. You were kind of not audible for a while. So
okay, I switched to a new network. I was using MTN and
after you switched, just like 1 minute ago.
I saw network fluctuate. Yeah, it's possible.
Okay, so we lost you at that point.
Okay. That means I need to rewind. So what I said at that point was that you need to take a section. If you look at the background here, you need to know if one system will work for the whole area. Let's say I'm designing for Lekki in Lagos. Lekki is almost a flat land, so I might not have any problem. So I can just go to the highest point and locate my elevator tank. In Abuja, it is not the same. Abuja will have like 6 zones, okay? So, and some zones in Abuja, they have to put a booster station. If the water comes from Lower Usman Dam, from using a 1.5 meter diameter pipe, that reduces to about 1 meter, 1.2, 1 meter as it gradates downstream, as it goes downstream. At some point, going towards Buzape, there's a booster station in one of the barracks. So when the water comes, the booster pump boosts it again because the water cannot go because that place is higher. We'll still come to that anyway. So I think that was what I was trying to explain. So zoning is important where one unit, one pressure, acceptable pressure zone is not workable. So as I said, what is the scenario? We are planning for we plan for 30 years because you don't plan for today, you plan for the future. And the parameters and the variable you use for your planning is the parameters of the future. So if I want to plan today, let's say for, let's say the current population of the place now is about, let's say 100,000. And in 25 years, in 30 years, I expect the population to grow to 150,000. The value that I'll use for my design will be 150,000. That's just the point. Then if I expect that there will be a new university, there will be a new school, there will be change of land use, and that change of land use can affect 20% of my development, then I'll calculate 20% of the population again and add it again, and that will be 170 now. So my final value, or what we call population equivalent, PE, which is a very important parameter for your design, will now change to 170. So 170 becomes my design, my baseline. Okay, so that's just what this thing is talking about. Then, when we did the design, it was obvious that the population in some areas in Germany then were going down. Others where we are moving. So, as an engineer, as a consultant, you also have to look at: is this place going to grow by what percent? Is it going to reduce by what percent? Is there going to be a change of land use in the next 50 years? Okay, that will help you. If you are piping to an industrial area, as soon as you get to industrial area, then your pipe size must increase, even though you can use a plug and lock it. So that in the future, when development gets to that point, they just come and open your plug use it from the manhole and then put in a new pipe and the thing will continue. This is where experience comes in. So the next thing you do, after you've done your background check and anything, you must move to the second most important thing. The first most important thing is to say, what is the population? What number of years am I designing for? And where am I going to locate my tank, which is the highest point anyway? The next question you're going to ask yourself now is, where am I getting the water? Is the water coming from groundwater? Is it coming from spring? Is it coming from surface water? Is it coming from another long distance water supply? Or is it coming from rainwater? So these are the water sources, or is it coming from surface water? All these water sources have their different requirements, their different costs associated with them. Groundwater is the best, is the neatest. Spring water, in fact, spring water is the best, followed by groundwater. Why is spring water better than groundwater? Because groundwater, you still need energy to pump it out, and that is cost. But for spring water is a well, is a groundwater under pressure. So you don't need pumping. It will just come out on its own because it is an artisan well. It's an artisan well, and an artisan well is a well whose pressure is above ground. An artisan well, or spring, as we call it as a layman calls it, is a groundwater or is a well whose pressure is above ground level. So it means the pressure is at the surface, okay? But groundwater, the pressure is still down there. So you need a pump to extract. Then we have the surface water. Surface water is the most expensive for treatment. Surface water requires a lot of water testing, sorry. It requires a lot of handling. And it requires it requires unique treatment processes, okay? It could be nanofiltration methods to treat it. It could be simple filtration method using filters. It could be using membrane technology. It could be using ion exchange. It could be using aeration, simple aeration. So there are different methods, but it depends on the constituent parameters that you want to treat. If the water is full of iron 2, the first thing you do is to aerate it. Bring in air, bring in oxygen. Oxygen is what you are bringing in, but oxygen is already 21% of air, okay? So you bring in air, the air will react with that iron 2 inside the water and make it insoluble, thereby converting it from iron 2 to iron 3. Iron 3 is partially soluble, insoluble, okay? In fact, it's partially soluble. Then you now introduce, after you've made it insoluble or partially insoluble, you now introduce what we call coagulants. Coagulants is the general word for all those chemicals that will form, that will make those iron 3 to become insoluble, okay? And then also make them to flocculate. Flocculate means they will now come together and form big masses, okay? Then when they now form big masses, you can now filtrate them using any kind of membrane or any kind of filter material. I take it again. If surface water contains iron, now I'm just talking about iron. If it contains nitrogen, nitrate, it comes in form of nitrate. There's a different way to treat it. If it contains sulfur, there's a different way to treat it. If it contains any trace elements, there are different methodologies to treat them. But the simplest one, which occurs 70% of the time, is the one that contains a lot of iron. Iron in form of iron silicates, iron, aluminum ion, and any other compound of iron, many of them. The simplest way to treat them is by aeration. That's the first step. And what does aeration do? What aeration does is basically to give him oxygen. If you remember our equation in school, if you give iron 2 plus, If you feed him with oxygen, it becomes 3+. And 3+ is not soluble in water. It floats. But floating is not enough. You now put sodium hydroxide, calcium hydroxide, aluminum sulfate, and many other chemicals. Those chemicals will go and replace those ions and make them flow. I'm not a chemist. I'm not good in chemistry, but that's what happened. The ion will now float. You now use filter. When I mean filter, the simplest filter is sand. Well-graded sand anyway. Rapid, slow sand filters. And you now use filter to filtrate them because they are not insoluble. Sometimes you can even decant them. When they pass through filtration bed, they can't pass through those filters. So the clean water will flow out. And then after flowing out, you can take them through other processes like UV to treat the microorganisms. There are many of them. Chlorination using chlorides, okay, which have been banned in many countries because of the odor and fear of being carcinogenic, okay? It can cause cancer. Okay, then your water source can also be a water supply from a long distance. In other words, it could be something from Lower Usman Dam in America, which is a bad thing anyway. Those in California, they go to the Gulf of Mexico, right? They go very far and they go and take water, and the water will flow in a channel, hundreds of kilometers until it gets inland. Then from inland, they will now treat it. Though they will treat it a little bit at the source, okay? But then now they treat it further. So water can also come from another long distance water supply. Then it can also come from rainwater, which we have not been practicing in Nigeria for now. But we're in water scarce country, rainwater is a variable source of water. So I've said two things. You have done your topography, determine the highest point, the lowest point, explain the topography, explain the area. You've looked at your water source, you've done your testings, you've seen the one that is best, you've developed the method for treatment. The next thing is you now start to reject the population. You put them into phases or catchments so that you know how to pipe to your piping or how to distribute the water. Okay, that's why if you come to Abuja, we have Wuse Guzape. Sorry, not Wuse Guzape. We have Gwarimpa, Jahi. We have Asokoro. We have Guzape. We have Gudu. These are the 6 water distribution area. Okay, so the same thing you do. If it's a large estate or a large place, you can also partition them into sections and then estimate their population. So here, the population today is 4,200, but the expected population at the end of my design period, is 6,300. Now, the second place is Forchley, it's a German one, don't mind it, is 950. In 25 years' time, in 30 years' time, it's going to be 1,200. So this is what you do. After that, you apply population equation. Nigeria is growing at the rate of 3.9% or thereabout. So you also have to look at the population of the place we're designing and come up with plausible values that can predict and project what the population will be at the end of the lifespan of your design. Then you don't do a water test of all the water areas, all the water tests. When I'm sending the material, I'll send us some UN standard, European standard for water quality so that we can read through within the week. So when we now did the tests for all the areas, these are the values we got. Okay. In doing water testing, there are 3 things you test for water: physical parameters, biological parameters, and chemical parameters. You test water for physical parameters, the chemical parameters, and biological parameters. In testing water for physical parameters, you look out for the turbidity. You look out for the turbidity. You look out for the color. You look out for, okay, let me share this one on our platform. So can you quickly go to the chat box? Let me just share this. It's something valuable. Of course, you can download it online. It's everywhere online. So for the physical parameters, it is the color, the conductivity, the turbidity, the resistivity, which is the inverse of the conductivity, and the smell, right? The smell, the odor, the physical conductivity, the turbidity, and what have you. Then, okay, so go to the chat box, is there now. So I can also open it now on my own. So this is what it is. So this is the water, drinking water point standard. So here, this is the German standard. This is the European Union standard. And this is the World Health Organization standard. So if you look down here, you see microbiological parameters. Here you have chemical parameters. Then here you have physicals, the bacteria, E. coli and the coliforms. E. coli is a very dangerous bacteria found in water that causes dysentery, what have you, what is it, cholera, diarrhea, okay? Then we have fungal. This is a German word, don't mind. But once you type online, say water quality parameters, you get them. Then the chemical parameters, we talk about nitrates. Nitrates comes from agricultural NPK fertilizers, agricultural things. Okay, they contaminate groundwater. Then we have fluoride. Fluoride is good, but too much of it causes problem with the teeth. Then we have nitrates. Nitrates can make the water to be acidic. Normally, water should have a pH of 7. Okay, so if there's too much nitrates, it might be, might be more alkaline or so. Then we have the color. Color should be under physical, but oh yeah, it's under physical. Yeah, it falls under physical. Then we have the physical parameters, the turbidity. Then you have the color. Then you have other organics in water. So this is something about that. Somebody say, where can we find the documents? I've sent it to your chat box. Go to your chat box, you can get it, sir. And as a designer too, please, I want to encourage us, and something I've learned newly. Everything you need is online. Just know how to search things on Google, and maybe get ready to pay small dollar if need be. If it's something that is worth paying for. Get everything. Okay, so that is that. I hope there's no question. We won't spend 1 hour. Okay, so you can see, so you can take your time and study this. Of course, this slide will be shared to you. You can take time and study. So we've done 4 things. Layout, topography, what does the area look like? After that, we look at the source of water. We established it. No, we did pressure zoning. After the topography, we're able to find out that, okay, it's not only one borehole source I need. I need to sink 3 boreholes at 3 different locations, not just one borehole in one location, which is not even ideal. Anyway, then you've measured, the next thing you measure the population of the people. And from the population, you say, okay, one industrial borehole will not do. I need to sink 4, 5, 6, 7, 8. Or surface water will not do. I need to do combined surface water, groundwater, rainwater, and what have you. Then the next thing, what is the quality of this source of water? You treat it, you do it. Then the next thing you now do is you now go into your layout and you now do your network, sorry. You now design your network. So in design your network, you look at the different areas. Use, Garki, Gwarimpa, Lekki, Ikoyi, Lagos Island, blah, blah, blah. You distribute them based on their population equivalent. You don't design based on one number. Okay? Even in an estate, you can design based on streets or phases. Phase 1, you do a design for them. Phase 2, you do a design for them. But even if you want to do one common design, then you must have a holding tank. The idea is for you to be able to, in case of maintenance, you don't shut down everybody. Okay? I know in Abuja, when they want to do some maintenance, they specify which area, and they just go turn off the valve. Okay? And ask those people to prepare water ahead of maintenance. And also, it helps you to do your calculation. If I know that people living in industrial north are 10,000 in population, I will know their pipe size. I will know how to define the pipe going to industrial north. If those in center are 2,000 in number, I will define their pipe going there. If people in camping area have a certain number, I will design their pipe based on that number. Are you with me? Now, this is something we're supposed to do next week, but let me just do it now. Okay? Let me do it now. To design any pipe for a water reticulation, you just need 3 parameters. You need the discharge. The discharge can also be called the demand, water demand. It can also be called the flow. It can also be called the water requirement, whatever. You can use any of these words interchangeably. They all mean the same thing, right? And that is called Q. I'm sorry, I'm doing this now. This is next week's work, because today we are doing introduction. Next week we'll start a calculation. But I'm just tempted to make it sink in. The next thing you need to do is, what is the slope of that area? Then the next thing you need is to say, what type of pipe am I using? That type of pipe, why you need the type of pipe is that you want to get what we call the frictional factor. So what kind of pipe am I going to use? Okay, so you need the demand, you need the slope, and then you need the pipe, the material of the pipe, because the smoother the pipe, the higher the flow. Then the slope, the more slopey an area is, the smaller the pipe size you need. But the major parameter, the most indispensable parameter is the discharge. Then how do you get the discharge of an area? What you do for discharge is very simple. Discharge is simply the water demand for one person. The demand for one person multiply by the number of persons. That's all. Then multiply by safety factor. Safety factor is always there. It's always, as an engineer, you cannot do a design without taking care of safety factor. It's almost impossible. Because you yourself, you can't be 100% sure of what you're designing. And you can't be sure that the end users will comply with your design. Okay? Those are known risk. Your known risk is that they might not even implement what you designed. They're just going to implement something else, but using values from your design. So even if they use some values on your design, they will still somehow fall within your professional advice, sort of. So now, all over the world, UN standard says water demand per person. WHO standard, WHO says one person requires 150 liters per person. We call it per capita anyway, per day. It means that one human being needs 150 liters of water. But the range is 100 to 150. In Nigeria, we're even using less. We're even using between 160 to 100, depending on whether it's local areas. Somebody raised his hand. He said, I'm not a water guy, but on shore, discharge and demand is the same. They are the same, sir.
Yeah, I have a question.
Trust me, sir.
Sorry, ahead, concerning the safety factor that you are talking about.
Sorry, sir?
If we have done concerning the safety factor that you are talking about, if we have done the projection of the population, do we still need to use the safety factor?
You use the safety factor for when you have gotten your demand, you now multiply it by your safety factor, just like we do in dam design.
Yeah, I understand what you are saying. I understand what you're saying. Well, if we are talking about the population now, if we have projected the population for the next 30 years, do we still need to use the safety factor again?
Yeah, you still use the safety factor, sir.
Okay.
Yeah. The reason is that the safety factor is a design parameter. What I mean by design parameter is that it affects the whole thing. It's like, meanwhile, safety factor is between 1.3 to 2.3. When based on German standard anyway, but it can be adapted to any design. So you have to choose between 1.3 to 2.3. Now, the higher the number of persons, the lower the safety factor. The lower the number of persons, the higher the safety factor. So safety factor, if you're a modeler, safety factor is those factors that helps you to take care of known and unknown. I always love to use that. In modeling, we call it externalities. Okay, it helps you to take care of the externalities. Externalities means something that beyond your control, external factors, in quotes. Okay, so it now depends on the population equivalent. You multiply by 2.3. As I said, Abuja, I think they designed Abuja for 1 million people. But those Germans are smart. And I'm happy for what they did. They use a safety factor of 2.3. So when I see people, they'll tell you that Abuja is 230 liters per capita per day. I know it's not true. As a water expert, I know it's not true. What they are seeing as 230 liters per person is actually 100 multiplied by a safety factor of 2.3. Okay. In fact, 2.3 is the German standard, and that's why I caught them. Okay, that's how I got to know. So somebody can tell you that I use 150 liters per capita. If you didn't see any other safety factor, why not also assume that you use 100, but you now use a safety factor of 1.5? That's engineering for you.
Okay. Thanks.
Me, right from when I was a junior designer, I know that if somebody asked me to do a bill, after doing my bill, I'll multiply by 1.2. Nobody taught me that one. Because I know that tomorrow, in fact, these days, if you ask me to do a bill, I'm going to multiply by 1.5. Because I know that between doing my design and you going to the Nigerian market, the price of things must have increased by 50%. Me, I'm sure of that one. Okay, let's continue. Now, and I would like us to do a small exercise now. That small exercise we're going to do is, I don't know if I've finished this. So in calculating your demand now, if I am, let me say my house now is a 3-bedroom bungalow. Okay. Whatever. Bungalow. Okay. And I let's tell people, use a population of 10 persons. Though people will say between 7 and 10. Use a population equivalent for a 3-bedroom bungalow of 3 to 10 persons. Okay. Then the water demand is 100 liters per capita per day. And I love to use a safety factor of 2.0 because I'm very lazy. I don't want too much calculation. Okay. So if I want to do the water requirements of where I'm staying, for instance, or where you are staying, a 3-bedroom, okay, to determine the value for 1 unit. So that if there are 100 units, I'll just multiply by a factor of 100, okay? Then if there are 1,000 houses in that layout, I'll just multiply the value of 1. But that will be if they are homogeneous anyway. If you miss all of them are 3-bedroom. So if let's do for 10, so that the calculation will be easy for us. So it means, from what I just said here, the water demand is 100. Now watch this calculation. Liters per capita per day. Sorry. Okay. I'll multiply it by the number of persons, and we'll say let's use 10. Then safety factor, let me use 2. why we always use a big safety factor is that in doing water design, we expect you to even have a 2 days. People talk about 2 day storage. Engineering is sweet, is interesting. These two here, some people will refer it as 2 day storage, but you as an engineer, as a water expert, it is not 2 day storage. It is a safety factor of 2. People will tell you that you are doing design, you are supposed to have water, like water that will be enough for you for 2 days before you pump. It's okay, that's a layman. But as a water expert, it's a safety factor. Okay, so if I multiply this now, what am I going to get? I'm going to get 2,000 liters per day. Capital have disappeared because I've multiplied by the capital, which is 10. Safety factor is unitless. Okay, so that means plus 2,000. That means for a household of 10 people, the minimum amount of water you need to give them is about 2 meters cubed per day. So if I'm now doing a 1 day storage, or what I call one day pumping, it means I pump only once in a day. It means I need to provide them with a tank size. This is just summary. Remember, later in the course, I'll show you how to calculate for tank. There's a better way to calculate for tank. Okay, but that will be if you know the consumption pattern of the area, which is difficult. So if this is 2, that means the thing will just be 2 meter cube tank, or the one we call 2,000 liters. All of us know 2,000 liters GP tank. 2,000 liters tank. But if I had used a safety factor of 1.5, meaning that when I have the storage, this number would have come to 1.5 GP tank. Then if I say I'm pumping twice per day, watch me now. If I say I'm going to pump, or what we call 12 hours pumping, it means after every 12 hours I go and pump water. Then it means that this value will reduce because one day is 24 hours. So if we're not talking about 12 hours, you know, we're going to do mathematics like this, 2 over 12 over 12, 24, that kind of thing. The summary of it is that it will give you something smaller, to give you something like 1,000 liters. It means every 12 hours, I'll go and fill my tank again. So when I get this value, that becomes the value I will use for my design. But for you to do your pipe sizing, you must reduce this 2,000 liters per day. You must reduce it into liters per second. Because in doing your discharge, you must reduce it to the smallest unit. And that smallest unit is the liters per second. There's no smaller unit than liter per second. Now, one day is 24 hours. 1 hour is 60 minutes. 60 minutes is 60 seconds. If you do this mathematics, you're going to get 8,400 seconds. So 1 day is equivalent of 86,400 seconds. Therefore, if I now want to convert this into liters per second, this will be important from next week. I know I'm bringing it on board. It means that the water demand per second, this one is 2,000 liters per day. You only use it for tank sizing. But for pipe sizing, you need it in the lowest limit, the lowest unit. And that's the lowest unit is liters per second. So here, it will now be 2,000 divided 8,600. So 2,000 divided 8,600. Sorry. It will give you 0.0231 liters per seconds. this becomes the value you use for further calculation. This is not the value from here now, from next week. Once you get this value, you're going to move to your charts, which I'm going to provide to us. You move to your charts, you now check the slope, the frictional factor, read it against this charge, the pipe size will come out. Any question? Mike, you're raising your hand.
Yes, actually I've been following with keen interest. And then sequel to a question that was asked initially, I need to also clarify this. Already in the 100 liters per capita per day, I want to believe that there's a factor of safety that covers loss, technical loss in that 100 liters per capita per day before it was actually arrived at. And now we are also introducing another factor of safety, which is probably 2.0.
Yeah, or 1.3.
Yes, yeah. Will it not actually give us something probably that is over design or something like that? Because along the line, I know whichever value we are getting, we'll still need to probably take care of all these technical losses, which probably we don't envisage have an issue. So how do we correlate that, please? Thank you.
You just use the word that I want to re-echo, over designing. In many infrastructure design, especially water or any underground design, it is advisable to over design than under design. Under design is a colossal loss. Over designing is just extra money. So to start with, over designing is allowed in water reticulation system because the system can only grow. You know, this is a great, in fact, when you finish your design, there's every tendency that your pipe, water will be flowing at 50% of your pipe, what we call depth of flow. Okay, it means if you put your pipe like this, water will be flowing at the center. But towards the end lifespan of a design, water will be flowing at say 70 or 90 or 90-something%. Now, what you said makes sense. We've already factored in some safety factor, but which you and I doesn't know in that 100 liters. Because that 100 liters is an assumption. It's an assumption. But this safety factor is also something that the code and standard specify that you should do. It's like what do I call it? It's like a requirement, a standard requirement that you should upscale whatever value you get. But then a range was given to you. So instead of you not introducing that safety factor, I would advise you maybe you lower it to 1.5, but you have to introduce it because the losses you have introduced are assumptions. These are assumptions without you taking into consideration the new location that is going to be used. Those that came up with 100 liters, they came up with as a generic value. But you will now introduce your own safety factor so that you can take care of the uniqueness or the exact uniqueness of where you're designing. Are you getting it? So safety factor, the second tier safety factor is necessary. And in terms of our designing, we shouldn't be afraid. But when we start our design proper, I also bring you to speed that even as much as our designing is allowed, there's a limit to it. So the standard says that your water should flow between 70 and 90%. Let me say it quickly, even though that we've not gone to that level. Water flow in your pipe must be between 70 to 90%. Don't go and design something and water will be flowing at 50%, less than 50%. You're a poor designer. What this simply means is, let me give you what this means. If this is your pipe, water flow should be between here and somewhere here. This should be the lower boundary, this should be the upper boundary, but it shouldn't be somewhere here. If water is here and then all this place is free, oh, sorry, I can't just, this is not AutoCAD. So, but I think some of us just got it. If this is your pipe, and you do your design at every point, level of water is here, you're a poor designer. The standard says that the water should be between 70, so it means it should be 70% full all the time, but it should not exceed 90%. Can someone tell me why it should not exceed 90%? Why should you not exceed 90%? So that there won't be surcharge.
Yeah, and then to give room for air trap, because pressure, yes, which definitely will be released via
because
if
it surcharges and that pipe breaks inside ground, what would you do? You can't even trace it. Problem. So that's it. Am I right? Okay. So let me go back to what I want to establish before that question came in. What I'm trying to establish at this point, I just want you to understand how you can compute the water demand per liter per day, because I just want us to treat this exercise now, very simple exercise, which because of time, may not really allow us to treat it. Maybe the physical training now, give us the time, everybody will treat it. This is industrial notes. When you see meter cube per day, what is it telling you? It means that we have multiplied, we've done what we just did now. When you see this value, 2,900 meter cube per day is the water demand of the people in industrial north, in the industrial zone. Swimming pool area requires 240.3 meter cube per day. This value now, you can convert it to liters per second. 1 meter cube is 1,000 liters. So what this thing is giving you an idea is the size of tank you will provide for that area. But the same size of tank is what you now downgrade. You downscale. When you downscale it into liters per second, you now use it to design the pipe that should be able to convey this level of water per day. I wish I can use a layman's example to really explain what I mean. Now, people living in industrial north requires 2,942 liters of water. What pipe size are you going to use to deliver that water every second? So all you need to do is to reduce this value to liters per second. And then you go up to your pipe charts and then you get it. That's exactly what I tried to do here. You can see how I converted it. At this point, I converted the 2 liters per day into the liters per day. So this is where you do it. This is where you do it. So with this now, you can see that if assuming now that there are 1,000 houses, stay with me now, stay with me. Assuming that this is a Ajay estate and there are 1,003 bedrooms in Ajay estate, the simple thing I will do is I'll just 1,000 times the requirement for one house. Gentlemen, that's what it is. So if I'm doing a meter cube, if I'm doing it in meter cube, watch what will happen now. Meter cube per day, Abi. So that will give me that the water requirement of the estate of Ajah or the city of Ajah is 2,000 meter cube per day. Then if I now want to do my pipe design, I will now convert this to liters per second. Of course, you know how I'm going to do it. Okay, I'll simply say 2,000 times 1,000, convert it to liters. And as soon as I do, I will introduce L. This is 2,000 M. There's a way we do it in science. If I put this one, I'll put over. I'll put M3. But let me not bore with those technicalities. So that M will cancel M3 will cancel M3. So when M3 cancel M3, you just have this left. Then divided by converting day. If I convert day to seconds, that's 8,600. Right? Somebody would have told me, why not just multiply 0.0231 by 1,000 instead of going on through this stress? Because that's the same value you're going to get anyway. But it's good that I do this so that those of us that have forgotten our mathematics will know that engineering, you can't leave your mathematics. So it's giving me 23.1. Is it not the same thing as multiplying that value? It does a second. So it means people living in Ajah, for them to get adequate water every second, there must be 23 liters, there must be a pipe that is discharging water at the rate of 23 liters for every second. So from next week, once I get this value, I'll go to what we call nomogram chart. There are many charts in the market, but my own is the one Once I get that value, I'll go to I'm going to send all these things. It's called nomogram charts. Why not just send it to us now? Okay, let me just send it quickly to our chat box. Now, there are three types. Depending on the type of pipe you are using. 0.1 is for PVC pipe. 0.4 is for ductile iron. 1.0 is for concrete pipe. All of us know that nobody's using concrete pipe. We'll come to sewage design after 3 weeks. We now know that, yes, you can use concrete to convey sewage. And therefore, you use that particular parameter. So, I'm trying to, okay. It's like you can't send two things, more than one thing at a time. You have to send it one by one. So now this nomogram is the one developed by University of Stuttgart. Please, if you go to the market, if you go to the internet, you see a lot of charts. When we're doing US Federal Highway Manual, okay, the one they use for sewer design, I will send us, but unfortunately it's in inches, so you have to do some conversion. But I expect at the end of the class, we can find on other charts online that can do pipe sizing for us. So many of them. Every university in the US have this chart on their own. Just imagine Stuttgart have their own. So you can imagine. I mean, these are things we can develop. I know there are some of our engineers that have developed them. Yes, people have done research on some of those things. Okay. So this is it. This is it. So, sorry, I don't know what it is again. So you can see how they got about this. This is how they got about this. So next week I will now show us this, and I'll just ask us to design this, design that, and can design all this stuff. Okay, we can design all this stuff. But let's we have time. We have time. Let's design them. So this is 2,948. Okay. Now, how they got this? How we got this is that we multiply population times water demand. So this is total water demand for this area. So if I now want to design the mains in a water recirculation system, you have like 3 or 4 tiers of pipes. You have the distribution pipe, transmission pipe. Transmission pipe is the one that takes water from source to elevated tank. Then we have primary line. Primary line is the one that runs along the street, the one that brings water along the streets. Then we have secondary line, the one that runs along substreets. And finally, we have the tertiary, which is the one that goes into your house. Okay. Somebody will forgive me, but let me open my AutoCAD and just show us the latest one of the designs that I can use. Let me just show us the visual, so that you know which one is the mains. So for this design now, all these pipes you see here are the main pipes or primary. These are the mains. So, and for many water recirculation systems, once you are able to design the mains, you have done your work. Yes, if you design the mains very well, the secondary, I don't get this now. The secondary and the tertiary are usually no problem. Okay, let me see if we can open. So if you design the mains now, like this mains now, this is the main pipe going to this area. When you get to these areas, there will not be other secondary pipes. Now, in water recirculation, if you get the primary pipe wrong, then you have rubbished the system. Because It's like, let me give you something that happens in our houses. That's why when you are on your tap, you have water, your neighbor will not have tap, even though I'm guilty of it also, I'm not done about it. The ideal pipe size to bring in water into a house is 2 inches pipe from the mains. Then once it enters the house, they cannot use 1.5 inch or 1 inch pipe. Because the mains is so important that if there is a pressure loss in the mains, the secondary are gone. So you can use a big pipe for the main pipe. Then the secondary pipe can just come using reducers and attach to the mains. So here, gentlemen, I have to close this. I think this is giving me problem. This is giving me problem. This is strange. Just stay with me. Okay. Industrial nodes with 2942 now means they've computed the population and the water demand. So our job will now be, if you reduce it to the barest minimum, we now go to our charts. Can we open those charts? So let me open the charts. I'm using a PVC pipe, so I can open the chart called the one with 0.1 frictional factor. Yeah, it is. It's the same thing. The transmission line is the bulky line supply. But it depends. It depends. Yeah, it could be. No, the bulky line supply looks like something that will be the primary. Something that looks like the primary. Engineer Brian, just go scroll up in the chart box. You see the charts. This is 1 out of 1,000 charts. As I said, in engineering, we make use of chart a lot. All of you will agree with me. You make use of chart a lot. I'm having a technical problem. I need to sort it out. Okay, here we go. Okay, this is what the chart looks like. Okay. This is what the chart looks like. On the horizontal, it is flow in liters per second, which is your discharge. On the horizontal, in the vertical, it is your slope. Then on this particular chart, you can see frictional losses in pressure pipes. K is 1.0. Okay, this is 1.0. Okay, 1.0 for concrete pipe, but that it doesn't mean anything. I'm having a problem. Just stay with me. Let me pause this record.